UAVs like the Global Hawk, MQ-9 Reaper, and new Loyal Wingman is the size. Prox Dynamics AS, the Norwegian company responsible for creating the Black Hornet, made it its mission to develop, produce, and sell the world's smallest and most advanced UAV. At just over the size of a soldier's finger, the miniature unmanned helicopter seems to have delivered on that promise. Of course, that small size means low weight, something for which soldiers on the ground are thankful. Between the load of ammunition, body armor, water, and other gear, a U.S. Army soldier is often carrying upwards of 60 pounds of equipment. Sometimes, according to NPR, that figure is closer to 100.
With the help of these flying machines called quadricopters, or quads for short. Quads have been around for a long time. The reason that they're so popular these days is because they're mechanically simple. By controlling the speeds of these four propellers, these machines can roll, pitch, yaw, and accelerate along their common orientation. On board are also a battery, a computer, various sensors, and wireless radios. Quads are extremely agile, but this agility comes at a cost. They are inherently unstable, and they need some form of automatic feedback control in order to be able to fly. So, how did it just do that? Cameras on the ceiling and a laptop serve as an indoor global positioning system. It's used to locate objects in the space that have these reflective markers on them. This data is then sent to another laptop that is running estimation and control algorithms, which in turn sends commands to the quad, which is also running estimation and control algorithms. The bulk of our research is algorithms. It's the magic that brings these machines to life. So how does one design the algorithms that create a machine athlete? We use something broadly called model-based design. We first capture the physics with a mathematical model of how the machines behave. We then use a branch of mathematics called control theory to analyze these models and also to synthesize algorithms for controlling them. For example, that's how we can make the quad hover. We first capture the dynamics with a set of differential equations. We then manipulate these equations with the help of control theory to create algorithms that stabilize the quad. Let me demonstrate the strength of this approach. Suppose that we want this quad to not only hover, but to also balance this pole. With a little bit of practice, it's pretty straightforward for a human being to do this, although we do have the advantage of having 2 feet on the ground and the use of our very versatile hands. It becomes a little bit more difficult when I only have 1 foot on the ground and when I don't use my hands. Notice how this pole has a reflective marker on top, which means that it can be located in the space. You can notice that this quad is making fine adjustments to keep the pole balanced. How did we design the algorithms to do this? We added the mathematical model of the pole to that of the quad. Once we have a model of the combined quad-pole system, we can use control theory to create algorithms for controlling it. Here you see that it's stable, and even if I give it little nudges, it goes back to the nice balanced position. We can also augment the model to include where we want the quad to be in space. Using this pointer, made out of reflective markers, I can point to where I want the quad to be in space, a fixed distance away from me. The key to these acrobatic maneuvers is algorithms, designed with the help of mathematical models and control theory. Let's tell the quad to come back here and let the pole drop, and I will next demonstrate the importance of understanding physical models and the workings of the physical world. Notice how the quad lost altitude when I put this glass of water on it. Unlike the balancing pole, I did not include the mathematical model of the glass in the system. In fact, the system doesn't even know that the glass of water is there. Like before, I can use the pointer to tell the quad where I want to be in space. Knowledge allows us to design novel machine architectures or to design clever